Welcome to section 9.3, which are parametric equations and derivatives. When they ask us to find dy over dx, that can be a little daunting, seeing how we have parametric equations. So we have x in terms of t and we have y in terms of t. Well, never fear, we can still find dy over dx. So what we're going to do is we're going to actually take the derivative of y with respect to t. So we're going to take this equation and we're going to find y prime in terms of t, and we're going to divide that by the derivative of x with respect to t. And then you can kind of see in that notation dy over dt divided by dx over dt, you can see how that notation fits into dy over dx. Well, that notation makes perfect sense. That's finding the first derivative. So remember, you find the first derivative when you need to find increasing, decreasing, relative extrema, instantaneous rates of change, all that good stuff. Second derivative, that's where we go to find concavity, points of inflection, that kind of thing. Well, when I go to find the derivative of the derivative, that means I need to find the derivative with respect to x of dy over dx. So that means we're going to take our first derivative and take the derivative of it with respect to t, and then go ahead and divide that by the derivative of x with respect to t. That way those dt's, you can see that those kind of, so to speak, cancel, and you would have your second derivative. So it's a little bit different than you might think. Okay, you're taking the derivative of the first derivative you just found and then dividing that again by dx over dt. So let's see what this is going to look like live and in person. So they may come right on out and tell you, please find the first derivative, please find the second derivative, but you know that's really not the way they roll. They ask us to find the slope and the concavity at the point 2, 3. All right, so we know we're going to have to find dy over dx because that is slope. Concavity, we're going to have to find the second derivative. Okay. All right, so x of t is really t to the 1/2 power. Y of t is really 1/4 tiered minus 1. So when I find my dx over dt, that's going to be 1/2 t to the negative 1/2 power, which is going to be 1 over 2t to the 1/2 power. When I go to find dy over dt, that's going to be 1/2 times t, or t over 1/2, or t over 2, sorry. So I've got the pieces I need. Now I'm going to find my derivative of y with respect to x. So dy over dx equals, I'm going to have my dy over dt, and I'm just going to continue to practice writing that. So for every problem I do in my homework, I'd like for you to write your dy over dt, your dx over dt. That way it's going to become second nature to you. Your dy over dt was 2 over t was 1 over 2t to the 1/2 power. So when I flip and multiply, I get 2t to the 1/2 over 1. So those 2's are going to cancel, and I have t to the 3/2. Now, the fun part about this is they want me to tell them what the slope is at the point 2, 3. Well, that's the x-coordinate and the y-coordinates value. You're probably noticing what the problem is. This is a t. It's not a y. It's not an x. So what we're going to do is we're going to find out what t would equal. I can either do that in using my y equation or using my x equation. The x equation looks a little easier, so what I'm going to do is I'm going to go ahead and use this guy. I know that my x-coordinate at this point we're asking about is 2, so I'm going to put 2 equals square root of t, and I'm going to solve for t. So t is going to equal 4. So when I evaluate my derivative, I'm going to evaluate it when t is equal to 4. So I'm going to have 4 to the 3/2 power. So the square root of 4 is 2. Take that to the 3rd power is 8. So my slope at the point 2, 3 is 8. Okay, well now I'm going to find the second derivative because I need to talk about concavity. So I need to find this guy, which means I'm going to have to find this guy and then divide it by dx over dt. Okay, so when I take the derivative of t to the 3/2, that's going to be 3/2 times t to the 1/2 power all over dx over dt, which is 1 over 2x to the 1/2 power. If I flip and multiply, I get 3t. Then when I evaluate that at that same value, so t is still 4, I get 12. Now, they didn't ask me what the second derivative's value is at 12, or at t equals 4. They didn't ask for the value, they asked what is it? What is the concavity? Well, if your second derivative is 12, that means it's positive, so therefore, it's concave up. Okay, so they did want to know the actual value of the first derivative because they asked for slope. Concavity, they wanted to know if it was concave up or concave down. Now, to put that in a parallel form, if they asked us, is it increasing or decreasing at the point 2, 3? Then we would have looked at this because it's a positive number, we would say that we were increasing. Okay? So what they want to know here is concavity. We are concave up. So the derivative wasn't too bad. So let's do that same concept with thetas involved. So if we're going to be finding dy over dx, that means we're going to be finding dy d theta over dx d theta. Okay, same concept, same amount of fun. Well, when I find dx over d theta, that's going to be -2 sine of theta. Y, so dy over d theta is going to be 4 cosine of theta. Plug them in and simplify away. So dy over d theta is 4 cosine. Dx d theta is -2 sine. Always try to make this look as nice as possible because remember, you are going to find the second derivative of this. So that would be -2 cotangent. That way I'm avoiding a quotient rule when I go to the next step. So that second derivative, remember, is going to be the derivative of my first derivative with respect to theta divided by dx over d theta. So the derivative of -2 cotangent is going to be +2 cosecant squared theta. Dx d theta is -2 sine. Okay. Well, those 2's are going to cancel out. I still have the negative, and you've got sine on the bottom. If I throw that up on top, that's going to be 1 over sine, which is cosecant. So I end up with -cosecant cubed. Okay. Now they didn't ask me to find any specific values, they just came right out and told me find the first derivative, find the second derivative. So that made it a little bit nicer. Alright, now in parametric equations they may ask us to find the arc length in parametric form. So if they give us a smooth curve C and they give it to us in that parametric form, now, such that that curve doesn't intersect itself on the interval from A to B, the interval from A to B, except at the endpoints, of course, so that just means comes full circle. Then the arc length of C over the interval is given by, so remember, these are nice smooth curves, so arc length, it's just that distance of that curve, so to speak. And if you look at the equation here, you've got the square root of something squared plus something squared. So it even kind of looks like the distance formula. Now, with our parametric equations, we are going to take the integral from a to b of the square root of our dx over dt squared plus dy over dt squared. So the derivative of our function of the x guy squared plus the y guy squared. All right, so let's see what it looks like live and in person. So this is our cute little curve denoted by the parametric equations. So I need to find dx dt first. Well, that's easy enough. That's going to be 2t. I need to find dy over dt. Well, that's even better. That's just 2. So when I go to find the integral from 0 to 2, because that's my a to b, 0 to 2, I'm going to do the square root of 2t squared plus 2 squared dt. Don't forget your differential there. So we're going to be using our calculator, so we don't really have to clean it up, but if you just have to because that's who you are, and apparently that's who I am, throw it in your calculator and away you go. Now, if you didn't get to use your calculator, how could we solve this? Think about that. So that is going to become 5.916. Now approximately, we're taking that to 3 decimal places just like we normally do. So to find an arc length of a parametric equation, not so bad. I'll see you in class tomorrow for lots of derivative fun.